Good morning, class, and welcome to another lecture in sustainable energy technology. In the previous class, we finished our discussion on hydroelectric power plants, and today we will start our discussion on wind power plants, where we are using the kinetic energy of wind to drive our wind turbines and generating electricity thereby. Wind energy is an emerging and rapidly growing area of renewable energy technology that has really exploded in the last 10-15 years. We will see this in the next set of data regarding this source of energy. So here in this plot, again taken from International Energy Agency's yearly publication of data, is the data on the world wind energy production by region in terawatt hours between 2005 and 2019. If you see, in 2005, the amount of total wind electricity production from wind energy was less than 100 terawatt hours, whereas in 2019, it has gone to around 1400 terawatt hours and has reached around 1500 terawatt hours by today this year. So what we see here is more than 15 to 16 times increase in the total wind energy based electricity generation throughout the world in a space of less than 20 years, around 15 years, 15, 16 or 18 years. So this kind of shows how rapidly electricity production from wind energy has grown. We can also see that initially most of the wind energy development was happening in the developed countries, the OECD countries, which includes Western Europe, USA, Japan, South Korea, etc. From 2010 onwards, we see an expansion in wind electricity production from China, and more recently from 2016 onwards, we see an expansion in non-OECD Asia, which means Southeast Asia, India, etc., as well as in the non-OECD American countries like Latin America, Brazil, etc. And this diversity in wind electricity generation by region can be seen in the relative strengths contribution of total wind energy production, wind electricity production between 2005 and 2019, where in 2005 over 90% of the total electricity generated from wind was from developed countries like Western Europe and USA and Japan, whereas today it's just 58%, whereas China contributes 28% of the total wind electricity production. Non-OECD Asia is around 6%, non-OECD Americas is around 5%. And you see the growth rate from 100 terawatt hours in 2005 to 1427 terawatt hours in 2019, which is around 14 times increase in a space of 15 years. If you see wind electricity generation on a country-wise data, then you can see that China has the largest, among all countries, China generates the largest amount of electricity from wind sources, which is around 406 terawatt hours, which is 28% of the total electricity generated by wind all over the world. Next up is the United States, which generates around 300 terawatt hours, which is around 21% of the total electricity generated from wind worldwide. Then you have Germany, and in the number 4th position is India. So in the recent few years, like in the space of last 6, 7, 8 years, India has also come up aggressively in wind electricity production. Then you have United Kingdom, Brazil, and other countries like Spain, France, Canada, etc. So this is the actual electricity that is being produced over the space of an year by a certain country. There is also another metric, which is the net installed capacity. What is the rated capacity of wind production country-wise for the different countries? Here also you can see China, US, Germany and India taking the first, second, third and fourth position respectively. So in 2019, the total electricity generated from wind was around 1427 terawatt hours and the net installed capacity was 623 gigawatts. This graph shows the rate of increase in wind energy capacity additions. So remember, this is the installed capacity. That is, if you think of a wind turbine, it has a rated power generation rate, okay, for a given wind turbine. So that rated power is its capacity. So if a turbine is rated at say 100 megawatts or 10 megawatts, that is the capacity of that turbine. You combine that throughout the country and you will get the total capacity of that country. And if you install a new wind farm, that new wind farm has a rated power production capacity, a rate at which, that is megajoules per second or kilojoules per second, at which it can produce electricity under rated conditions. We will discuss what rated conditions mean in terms of wind energy, but just as we discussed during the hydroelectricity generation also, there is a rated flow of wind for which the turbine is designed around. That is the point at which the turbine is operating at maximum efficiency. So the corresponding power is the rated power and that is the rated capacity of that turbine. So here we see the capacity additions year-wise worldwide for wind power plants. And you can see that the capacity additions have actually continued to increase over time. So whereas in 2011, 2012, 2013, the capacity additions hovered between 40 to around 50 gigawatts, by 2018, 2019, 2020 and 2021, the capacity additions have actually doubled to around 95 to 102 gigawatts. So clearly, the rate of growth of wind energy through additional wind farm installations have also increased worldwide. So the rate of growth of wind turbine electricity generation capacity is actually increasing still at a very rapid rate. And this has been spurred by the decrease in the total cost of electricity generation from wind energy. So as we discussed, this is the levelized cost of electricity in US dollars per megawatt hour. So how much money it takes to generate 1 megawatt hour of electrical energy from a wind farm. Okay, so that is the levelized cost of electricity generation from a wind farm. And you average it for all the world and you can get the levelized cost of electricity of wind turbines that has been installed on that year. Okay, and you can see that the levelized cost of electricity has decreased from around 85 to around $50 per megawatt hour for onshore wind turbines, and it has decreased from around $180 to around $120 for offshore wind farms. So clearly you are seeing a decrease in cost within an 8-year period, and if you see the trends even earlier, the trend will be even more starker. There has been a steady decrease in the cost of electricity generation from wind energy sources, and this has been spurred by efficiency improvements, technological developments, improved materials, improved mass production capabilities, etc. So as the cost of electricity generation has decreased, it has become more economically feasible to generate wind energy at lower and lower costs, and which makes it competitive with other sources of electricity like fossil fuel sources, and hence more and more countries and companies are switching to installing wind power plants rather than other sources of energy, and that is spurring the growth of wind energy generation. So that is the global and the economic angle which shows why and how the wind electricity generation is happening. So now we will look at wind energy as a resource and how do we actually tap wind energy through wind turbines. Okay. So here in this slide we are discussing how much wind energy resource is actually available for us to tap. Okay. So of course there is a finite amount of air in the atmosphere which is blowing at finite velocities. So based on that you can calculate how much is the total available kinetic energy in the flow of air throughout our atmosphere. Okay. So the idea here is this. Fundamentally, wind energy is the kinetic energy of wind is driven by solar radiation. How? Solar radiation heats up the atmosphere and the earth. Differential heating of the atmosphere causes pressure gradients and the wind flows across these pressure gradients. Correct. So actually the thermal energy that is present in the atmosphere is converted into kinetic energy of winds. So if you think of the total energy of the sun that is available on earth, that is around 3.46 into 10 to the power 12 kilowatts. Approximately, and it has been estimated by physicists, around 2% of this solar radiation is converted by differential heating to wind power, as we discussed. So the total mechanical energy of wind, if you take 2% of this and then convert it into what is available throughout the year. This is kilojoules per second. So you have so many seconds in a year. So you can get the amount of energy in joules and then you can multiply it by 0.02 and you will get around 1.1 into 10 to the power 23 joules of energy per year. So that is an extremely large amount. So there is a huge amount of mechanical energy in winds that is available in Earth's atmosphere, around 10 to the power 23 joules per year. Unfortunately, most of this wind energy is inaccessible to human beings given our current technological abilities. Okay. So because most of it is located in the high troposphere or far out in the oceans. So you can think of it like this, that a lot of these wind flows are happening at like 2, 3, 4 kilometer altitudes. Okay. Clearly we cannot have turbines that operates at that high altitudes. Okay. And also a large amount of this wind energy is basically winds that are blowing over oceans far away from land, in the middle of Pacific, middle of Atlantic, middle of the Indian Ocean. Okay. A lot of it may be also blowing over Antarctica. Okay. So these places are inaccessible to human beings. Winds near the ocean, in deep oceanic areas, winds at very high altitudes, winds in Antarctica, etc. So you eliminate those wind sources and then the technologically accessible wind power is around 300 into 10 to the power 6 gigawatt hours per year. You can again convert this into joules and see what percent this is. Okay, you can just do that by converting gigawatt hour into joules. But this estimate is around 300 into 10 to the power 6 gigawatt hour of wind energy is accessible throughout the year for human technological usage, okay, to be converted into electricity. Now of this, wind energy is actually quite unevenly distributed. Highest wind energy resource usually exists in the mountains and in offshore regions. So close to the shorelines where there is oceans also, but it's close enough to the shorelines that humans can tap it. That is a location where a lot of wind energy is concentrated. And also high wind velocities are seen in high altitude regions like high mountains, high plateaus, etc. Also, wind speed is seen to increase at high latitudes and is low near the tropics and on land. So there is a distribution that if you go higher up in latitudes as well, so like 60 degree north, 60 degree south, 70 degree north, 70 degree south, there also the average velocity of wind is greater than in the lower latitudes, that is around near the equators, near the subtropics, etc. So high latitude countries have a greater access to wind energy than low latitude countries. And also we should note, in terms of our location, southern India and western India have moderate to good wind energy resource. So let's look at the wind resource that is accessible to us, firstly on land, and then we will look into oceans. So this is the onshore wind power map. Okay, and this is wind power given in watt per meter square. So even in a square meter of area, how much wind energy is available on land near the surface of that land area. Okay, so we are not discussing 2 kilometer above, maybe 100 within the 0 to 100 meter region, which is the typical height of a wind turbine. Okay, how much wind power is available per meter square of area on land in different parts of the world. So here you can see that the deep blue are regions where the available wind power is extremely low, while deep red regions are where available wind energy is extremely high. In between, like yellow and orange, you have moderately high wind energy, whereas green and light blue are moderately low wind energy. Okay. And now you can see that if you look into the tropical region, so this is the tropical region, everywhere near the tropical regions on land, wind energy values are quite low. So it's between 0 to 1.2 at max for most of these regions. Okay. Whereas if you go to higher latitudes, like above Tropic of Cancer, so in northern Europe, northern USA, Canada, higher regions of Russia, Australia, southern tip of South America, etc., you will see that the wind energy available consistently increases. This shows that higher the latitude, higher the amount of wind energy that is available in those regions. Okay. Second is that typically, though this is not necessarily true, coastal regions and islands have higher wind energy. Okay, because ocean wind velocities in oceans are much higher than wind velocities in the land. Okay, the reason is that the ocean surface has much lower friction compared to land surfaces. So wind slows down drastically as it hits land. This is very good for us when you think of tornadoes and cyclones, but somewhat bad for us when you think of using the wind to use in wind turbine systems. Okay. So you can see inland, Iceland, these are extremely has very high wind energy resource, because these are not only islands, but they are islands that exist at higher latitudes. So in UK, you will see a lot of push to develop wind energy, because UK has a higher available wind power throughout its area. Similarly, Japan's northern area has higher wind energy. Okay. Australia, because it is surrounded by lots of oceans and is a smaller landmass, also has higher wind energy in certain regions. Okay. Sri Lanka, you can see, has higher wind energy. Peninsular India, because it's surrounded by ocean, also has somewhat higher wind energy compared to interior of India. Right. So that kind of a thing exists. A second part of it is high altitude places, mountains, high plateaus also have higher wind energy. So you can see this in the Tibetan plateau region, which is extremely high plateau region. So this region also has very high wind energies. Okay. So typically plateau regions are also there. Say here in the Ethiopian region, it has a high plateau. You will have a higher wind energy. The interiors of Mongolian region, which has a extremely flat, high terrain, it also has very high amounts of wind energy. Plateau regions in US Central also have high amounts of wind energy. Okay, so high plateaus, close to coasts, islands, high latitudes, these are all have high amount of wind energy available onshore. Now notice that the wind power availability on land at least ranges from 0 to 7.2. Now what is the wind power availability on the oceans? This is the offshore wind power map, and you can see that the wind power availability here starts from 30 watt per meter square and extends up to 1400 watts per meter square. Okay. Here it ends at 7 watts per meter square. So wind energy available near the surface of the oceans is 10 to 100 times, if not more than wind energy available on land. That is why offshore regions are so attractive for wind power development because you are getting much higher densities of wind power that you can extract. Of course, if you see here, most of the regions near the coasts have blue or this black, deep purple, showing that the coastal oceans have lower wind power because the wind is reaching the land and it is already feeling the frictional deceleration effect. Regardless of that, at most places in the coasts, you are getting 30 to 190, for example, wind power availability. Okay, in watt per meter square, which is significantly higher than any land area can provide. However, wind power really picks up in the deeper regions of the oceans and especially in the high latitudes. So you see high latitude oceans in northern Pacific, northern Atlantic, southern Pacific, southern Indian Ocean, southern Atlantic have wind powers that are going to 1400, 1000, 850 watt per meter square. Okay. In comparison, low latitude oceans have lower wind power even deep in far away from the coasts, around 350, 450, 550, like that. Okay. Still, you can see how much wind energy is available in the oceans compared to land. Okay. It's also one of the reasons why it was possible to have sailing ships sail at all before the era of mechanized ships. Okay. You cannot actually travel on land with the available wind energy that is there. But because oceans have higher wind velocities, you can actually move ships which were quite big for their time using wind power. Now let's look at the wind resource in India in a little bit more detail. Here, instead of wind power, we are looking at the mean wind speed map at 100 meters above the land, So 100 meters above the ground. Okay. And blue region is low winds between 2 to 3 meters per second. Green regions are moderately low winds between 3 to 4 meters per second. Yellow regions are moderate winds between 4.5 to around 5.5 meters per second. Orange region is moderately high winds 5 to 6 and red regions is above 6.5 very high winds. Okay. Now you can see certain regions where you have a large average wind velocity. This is the Ladakh area of India, and this region has high wind velocities because it's part of the Tibetan Plateau. Okay, it's firstly it's high altitude and hence you have high wind speeds going above 7 meters per second. So Ladakh area has a large potential of wind farm development. Similarly, Gujarat area, entire the Saurashtra Plateau, Saurashtra Peninsula area has consistently high wind speeds of around 5 to 7 meters per second. Another region with high wind speeds is the Deccan Plateau. Again, high region, Deccan Plateau altitude is significantly higher than other parts of northern India. So this entire Telangana, Andhra Pradesh, Maharashtrian Plateau, parts of Karnataka see high wind speeds going up to 6.5 meters per second. Also, the offshore region of the eastern India sees very high wind speeds of around 7 meters per second. So these regions, as well as offshore regions of the coast of Gujarat and northern Maharashtra, also see very high wind speeds. So these are some of the regions where it is economically feasible to develop wind farms. So if you think of where to place wind farms in India, some of the states will be Gujarat, Maharashtra, Telangana, Karnataka, Tamil Nadu, coasts of Orissa, Andhra Pradesh, Tamil Nadu, etc., as well as the Ladakh area. In contrast, the Indo-Gangetic plain, that is moving from Punjab to West Bengal and going into Assam and the northeast, shows very low wind speeds. Okay. So these are not good places to put your wind turbines. Now let us look at something of how wind velocity is related to the available wind power in a given region, because we can measure wind velocity. So given a wind velocity, what is the total wind power available in that region? How do we calculate that?